constraint optimization problem. So we minimize with respect to x, which is in n dimensions, the function f of x subject to the inequality constraints gix is less than equal to 0. I belongs to script I. This is the set of equality constraints. And hjx is equal to 0, where j belongs to E, script E, that's the set of equality constraints. The Lagrangian for this constraint optimization problem is f of x plus summation lambda I gi of x. This term corresponds to the inequality constraints, and lambda i's are the Lagrange multipliers or dual variables for the inequality constraints. And the third term is summation j mu j hj of x. Mu j's are again Lagrange multipliers, but they correspond to the equality constraints. The Lagrange multipliers lambda i's that are for the inequality constraints must be greater than or equal to 0. There is no such constraint for the mu j's. The constraint optimization problem can be expressed more concisely using vector functions. So gx is less than or equal to 0, where this g is a vector function, Boji, of inequality constraints, which is a mapping from n dimensions to L dimensions, where L is the cardinality of the set of inequality constraints. Likewise, hx is equal to 0, where h contains all the equality constraints. It's a vector function that maps the n dimensions to m dimensions, where m is the cardinality of the set of equality constraints. The Lagrangian for this COP can now be expressed more succinctly too as f of x plus lambda transpose g of x plus mu transpose h of x, where lambda and mu are vectors. The feasible set F is the set of all points x that are feasible, that is, for all I in the set of inequality constraints, gi of x is less than or equal to 0, and for all j belongs to the set of equality constraints, hj of x is equal to 0. The primal function is theta p of x, which is supremum with respect to the dual variables lambda greater than or equal to 0 and mu of the Lagrangian, which is supremum of f of x plus lambda transpose g of x plus mu transpose h of x. And expressing the Lagrangian as scalars, this is supremum with respect to lambda I greater than or equal to 0 and mu j of f of x plus summation lambda I gi of x plus summation mu j hj of x. There's a slight misuse of notation here. This lambda I greater than or equal to 0 means that we're carrying out the supremum over all possible lambda i's greater than or equal to 0 and over all possible mu j's. In fact, all possible dual variables. Therefore, we are eliminating lambdas and mu's. By doing the supremum over them, we are eliminating lambdas and mu's from the Lagrangian, and that gives us a function of only x. So theta p of x is a function of x. It's not a function of the lambdas and mu's. Therefore, theta p is a mapping from n dimensions to the real line, which is the same as the objective function. A mapping from n dimensions to the real line, because the only argument to theta p of x is x, since lambdas and mu's have been eliminated. Now, since this is an important expression, let's highlight it. So in the Dual, what we do is, it's a function, theta d is a function of the dual variables, lambda and mu. We eliminate the primal variable x from the Lagrangian by taking the infimum with respect to x. Therefore, theta d is equal to infimum over x of fx plus lambda transpose gx plus mu transpose hx. And I've scalarized it in the next line. So lambda transpose gx gives us summation over I of lambda I gi of x, and mu transpose hx gives us summation j mu j hj of x. And theta d is a mapping from R L plus m to the real line. Why is that? Because it's a function of lambda and mu, and we have L number of inequality constraints, which is the same as the dimensionality of lambda, and we have m number of equality constraints, which is the same as the dimensionality of mu. Therefore, the domain of theta d, the dual function, will be L plus m dimensional. And the range is the real line because it maps to a scalar. We shall look at different theorems here without proofs, just the statements. The first one is the dual function is concave. What does concavity mean? It means that it's inverted cup shaped. And so what property does it satisfy? Given any 2 points, here it's lambda 1 and lambda 2, the function of the convex combination is greater than equal to the convex combination of the functions of the 2 points. And the dual function is concave with respect to lambda. It's also concave with respect to mu. Weak duality. The maximum of the dual is less than or equal to the minimum of the primal. Theta d star is less than equal to theta p star. This always holds true. And the proof of this theorem is quite trivial if you invoke the well-known minimax theorem. The supremum of the infimum of a function is less than equal to the infimum of the supremum of a function. Theorem, strong duality. If the objective function f and all inequality constraint function gi are convex, and all equality constraint functions hj are affine, and Slater's condition is satisfied, then strong duality holds. So these are the conditions that needs to be satisfied. The function f must be convex. Each gi of x must also be convex. The hj of x must be affine. And this is Slater's condition. So there must exist a point x naught such that gi of x naught is strictly less than 0. The inequality constraint is strictly satisfied. And hj equals 0. The equality constraints have to be satisfied. Then theta p star equals theta d star. The duality gap is 0. So let's review the primal and the dual problems. In the primal problem, so what we have is theta p of x is the primal function, and that's the supremum with respect to the dual variables of the Lagrangian. So we are removing the dual variables from the Lagrangian by carrying out the supremum operator, and that gives us the primal function, which is a function of only the primal variable x. And the minimum of the primal function is at x star. This schematic shows theta p of x, the blue curve. And remember that in the infeasible region, theta p of x is infinite. So let's pretend that the left side and right side of this shaded region are infeasible. Then theta p of x would go to infinite on both sides, and it stays equal to the objective function in the feasible region. So this blue curve also represents part of the objective function. And this is the minimum of the primal function, theta p, and that's theta p star. So in other words, this point here will be x star. Dual. The dual function theta d lambda mu is the infimum of the Lagrangian with respect to the primal variable x. So we are removing the primal variable from x by taking the infimum with respect to it of the Lagrangian, and that gives us theta d, which is a function of only the dual variables. And the supremum or the maximum of the function theta d occurs at lambda star mu star. In this schematic, the dual function theta d is shown by this red curve. It's always concave, as we have seen, and just for simplicity, I've used this axis to represent both lambda and mu. And this is theta d star, where theta d lambda mu, the dual function, acquires its maximum value at theta d star. So this would be this point here. Let me use another color. This point here would be lambda star mu star. And duality gap says that theta p star is more than theta d star. Theta p of x is always above theta d of lambda mu. Now, why do we use the dual of a constraint optimization problem? There are several reasons for this. Sometimes it's algorithmically simpler to solve the dual, either because we have less number of constraints. So lambda and mu, the dimensionality of lambda and mu are together less than that of the dimensionality of x. So that makes it simpler to solve. Otherwise, you get simpler equations to solve the dual. And another thing is it's always concave, even if the objective function is not convex. So there's no guarantee that the theta p would be convex. Even if that's the case, theta d is concave. And so you can employ simpler algorithms to obtain theta d. And under certain circumstances, the duality gap is 0. When you hit the maximum of the dual, that's the saddle point, you automatically get the solution. And even if strong duality does not hold, it's always attractive to look at the dual, because it would tell you, if you're using the primal function, the duality gap will keep decreasing, and it'll tell you how close you are to the optimum of the primal. And of course, when strong duality holds, then we have a point called the saddle point, x star lambda star mu star. That's this point here.